So last time, we started to calculate spatial correlation functions, Gij, for a one-dimensional Ising chain. So today, we continue this calculation, and in particular, last time, we defined this Gij as this average of the Si.Sj, subject from the product of each individual expression value of the Si and Sj, and for a one-dimensional Ising chain, at any finite temperature, we know that there's no spin moment after ensemble average, so it is effectively simply just the ensemble average of Si.Sj. And we can also rewrite this Gij in terms of the deviation from this expression value of Si and Sj, and we could take a product of these deviations of this Si and Sj. We call this delta Si and delta Sj. And the correlator Gij is nothing but the correlation function of delta Si and times delta Sj. Because you could expand this product of these two brackets and you get back to this formal definition of Gij. And last time we also introduced another function called Pij, which is a probability that the spins on side I and j have the same value. So what is the probability that the Si and Sj have the same sign or same value? And we define this as an average of this delta Si Sj, which is 1/2 of times 1 plus Si.Sj, which is related to the Gij from this expression here. So in particular, Pij gives you 1 if Si has the same value of this Sj, and it gives you 0 if Si is minus Sj. So, and we will use that definitions and interpretations to understand how the spins on the Ising chain are related to each other if they are not at the same site. And previously, we calculated the nearest neighbor spatial correlations of the spins Si.Si plus 1 after ensemble average, and it is given by hyperbolic tangent function of Ki. And in the case of isotropic homogeneous Ising couplings, the nearest neighbor Ising coupling, so all those Ki's are uniform, are the same, so which is given by beta times j. And we know from last lecture that this spatial correlation between nearest neighbor spins approaches 1 in the ordered phase and 0 in the disordered phase. So mathematically, the way that we obtain the calculus Si.Sj is given by the derivative of the partition function with respect to this reduced coupling Ki, and altogether divided by this partition function. So what about the second neighbor correlation functions of the Ising spins, namely the ensemble average of Si.Si plus 2, for example, and we could take advantage of what we learned from this nearest neighbor spatial correlations, and we keep calculating the relation between the spin on side I and the spin on side I plus 2. And because we know the spatial correlation of spins on side I and I plus 1, and also we know the correlation between spins on side I plus 1 and I plus 2, and we could take advantage of what we learned for the nearest neighbor spin correlations, and we get the second neighbor spin correlations. While to compute this, we could again make the best use of this nearest neighbor spin correlation, and we take the second derivative of the partition functions back to the couplings with respect to Ki and Ki plus 1 respectively, and we divide everything by the partition function. And if we do so, you could easily calculate this second derivative of the partition function with respect to couplings, and you get 4 spins inside this ensemble average, and these 4 are Si, Si plus 1, Si plus 1, and Si plus 2. And then we could simply rearrange all these spins because they are simply just plus or minus 1. So you get si plus 2 times si plus 1 squared. And we know the Ising spins can only have two values, plus or minus 1. So in either case, if you square the spin, the Ising spin, you get 1. So you simply just get rid of this si plus 1 squared and consider this simply just 1, and you remove the two spins away from this second neighbor correlation function. So you get the si plus 2, which is exactly what we want. Okay, so the lesson we learned here is that to get this second neighbor's spin correlation function, we need to take a second order derivative of the partition function with respect to the coupling constant and divide it by this partition function. But what we know is that this is simply just a product of this two nearest neighbor spatial correlations of the spins if you really calculate this second derivative of the partition function. By taking advantage of this nearest neighbor spin correlations, you could simply just make a product of this hyperbolic tangent for site I and for site I plus 1. So then you get simply just a product of these two hyperbolic tangents. And you could generalize this calculation to J's neighbor correlation functions of the spins, and which is si dot si plus j ensemble average. And this is simply just j minus 1th derivative of the partition function with respect to the coupling constant and divided by this partition function. So you could take advantage of this nearest neighbor spin correlator, and you could generalize to gi I plus j as the product of all these hyperbolic tangents from the side I to side I plus j minus 1. And you set all this coupling constant uniform. As a result, the spatial correlations of the Ising spin on any given two sides between any given two sides I plus j is given by hyperbolic tangent to the power of hyperbolic tangent k to the power of j. And this is simply just a function of the distance between Ri and I plus j. Okay, because this is a function of only j, which is the distance between I plus j and I. So now you get a very good intuition here that the correlation function, the spatial correlation function of the Ising spins between any side I and j is a function of the distance between these two sides. And in particular, in the one-dimensional Ising system, this correlation function is actually the hyperbolic tangent of this coupling constant k to the power of j, where j is the difference between these two sides. Okay, and therefore you could calculate any, the relation of the two spins at any given site. Okay, so you could calculate whether these two spins on different sides of the chain have the same value or not. Or what is the probability to find that they have the same sign or not the same sign? So let's take a short break, and we'll come back. We will continue finishing this calculation to consider the existence of long-range magnetic order from this analytical structure of this Gij. But before we stop, let me just make a short comment. So when you take the second derivative of this partition function, you're going to take advantage of the nearest neighbor spin correlation functions when you evaluate this ensemble average. And that will lead to the two hyperbolic tangent function of the coupling constant. So I leave this kind of a detail to you as an exercise, not a homework, but you could practice and repeat this calculation at home. Okay, so let's take a short break. Let's continue. So we just arrived the general analytic expressions of spin-spin correlations at different any given two sides I and I plus j. So this is I and this is I plus j. And the correlation function depends only on the distance between these two sides. Namely, it depends only on the hyperbolic tangent of k to the power of j, where j is the distance between these two sides. And we could use that analytical general form to find whether we have a phase transition at 0 or final temperature, whether the states at 0 temperature, high temperature shows a long-range order. So let's just look at the simplest limit, which is 0 temperature limit. When temperature is 0, we know that K is actually beta times J. When T goes 0, beta, which is 1 over kBT, goes infinity. And for any given finite coupling J, K should go to infinity. So when K goes to infinity, this hyperbolic tangent of K, where K goes to infinity, is actually 1. Remember this function as a function of K. Remember that this is kind of this is hyperbolic tangent of K to the power of J. So when K goes to infinity here, and this hyperbolic tangent goes to 1, and if you simply just take a J's power of hyperbolic tangent, it certainly goes to 1 even faster. So which means that if you look at this probability function Pij, which defined earlier, and you can see that the probability to have this Si, the same value as J, is actually 1, which means that you get a 100% probability to have two spins on these two sides have the same value. And this is true for any arbitrary psi j or psi I plus j, and where j is actually arbitrary, okay, which means that this j could be the nearest neighbor or next nearest neighbor or third neighbor and so on. So it doesn't matter how far the second spin from this first spin at side I. So in other words, the spins along the chains, no matter how far they are apart, they all have the same sign or same value, and that is what we know they are ordered, or they have the long-range order. The meaning of the long range refers to the fact that over a long distance, the spins, even though they are far away from each other, they also have some correlations. They have finite probability to have the same value, and that probability is actually almost 100%. So in other words, they have this long-range correlations. No matter how far away they are, they always have the same values for the spin. So we have two degenerate ferromagnetic ground state for the Ising model. One is all spin up, another is all spins down, and that's the ground state at 0 temperature of the Ising chain. And we exactly and analytically derive such a conclusion that all spins should point to the same direction because the correlation function of these two spins on different sides approaches 1 in that limit. It's very easy to understand and very intuitive results. So let's look at this finite temperature behavior of the same correlation function. Suppose that temperature is finite and positive, then we know that hyperbolic tangent of K should be less than 1, and then hyperbolic cotangent of K is actually greater than 1. Therefore, we could rewrite this correlation function in a way that it shows exponential decay function, where this is given by e to the minus j times the log of a cotangent of K is actually bigger than 1. You get the log of this hyperbolic cotangent of K, and therefore the log of a cotangent of K is actually positive. Okay? And also the j is actually positive because this is just a psi index. And therefore this is an exponential decay function. Remember, this is a minus sign in the exponent here. And in particular, we can define a length scale called correlation length, C, which is 1 over this log of a hyperbolic cotangent of K, okay, which is exactly inverse of this stuff. And this defines a length scale over which the spins are correlated with the probability almost 1. Okay? So you can see how far away of the two spins that are correlated with each other. So for example, if you measure this correlation of these two spins on side I and I plus j, for example, and if they are correlated, meaning they have the same value, probability that they have the same value is almost 1. But if you calculate the correlation for even longer distance, for example, this is, say, I plus 10 times j, for example, then you may find that this correlation function decreases to almost 0. This is just some hypothetical thinking or some kind of possibilities. So for some system, if you have this perfect correlations over some range of your system in spatial dimension, then you call this length scale a correlation length. And if these two particles or two spins are far away from or go beyond this correlation length, then you don't have such a correlation between them. Okay? In such a case, we call this spatial range or length scale over which that spins are perfectly correlated, the correlation length. So any distance beyond the correlation length, we don't have such a correlation between the observables, such as the spin-spin correlation function. But near the phase transition, as we mentioned earlier, the correlation length diverges. Okay? This is exactly what happened here. If you look at this correlation length as 1 over log of hyperbolic cotangent of k, when k goes to infinity, this hyperbolic cotangent of k is actually what? 0. Therefore, you get the infinity of the correlation length. But at any given finite temperature, T positive but k is finite, then this function log of hyperbolic cotangent of k takes this form, e to the 2k divided by 2. When temperature is actually finite but low, then this correlation length goes as e to the power of j divided by kBt. So you can see that when temperature T approaches 0 from above, then this number, this value diverges exponentially, which means that as temperature goes to 0, then the correlation length diverges exponentially. And this indicates that transition temperature is exactly at T equals 0, which means that Tc is actually 0 because, as we already mentioned, that when phase transition occurs, the correlation length diverges, which means that no matter how far away these two particles, two spins are located, they all have the same correlation. They are all correlated in a power law fashion or other fashion. But here, the correlation length diverges exponentially, which is not a conventional form. So usually, in critical phenomena, the correlation length diverges in a power law fashion with a power law exponent nu associated with that power law divergence. Okay, so in other words, the correlation length goes to infinity in a power law fashion. But here, in the one-dimensional Ising model, the correlation length diverges exponentially. So this is a very special case of a phase transition. And in some cases, we have such a very rare situation where correlation length diverges exponentially. And at the end of the semester, we may have some time to discuss the Kosterlitz-Thouless phase transition, or the KT phase transition, that occur in the two-dimensional superconductors at finite temperatures. In that case, the correlation length really diverges exponentially. We need to be aware that this doesn't usually happen for many other critical systems. And most systems shows critical phenomena. In those systems, the correlation length diverges in a power law fashion. Okay, so finally, let me just make some remark. Number one, correlation length cannot diverge unless lambda 1 is the same as lambda 2, as we mentioned already. So therefore, no phase transition occurs unless the degenerate eigenvalue occurs. And number two, in the presence of the field and lambda 1 is greater than lambda 2, and no phase transition occurs for any finite field. And number three, in the zero field limit, and we have the degenerate eigenvalues when k goes to infinity or t goes to 0, and we have a phase transition exactly at 0 temperature and 0 field limit. Okay, so these two remarks summarize what we derived over this last few lecture hours. Correlation length diverges only at the transition, in this case, only in the limit of 0 temperature and 0 field, and no phase transition occurs unless we have a degenerate eigenvalues, which does not occur at any given finite field. And the 0 field and 0 temperature limit, these two eigenvalues are degenerate, and therefore we have a phase transition. And to tell whether we are close to phase transition, we could calculate and monitor the correlation length and see whether this correlation length diverges. If the correlation length diverges, this implies that no matter how far these two spins are located, they all feel that they are correlated. It's like the Ising ferromagnetic ground state, that no matter how far these two spins are away from each other, they are all pointing up or pointing down, and the location of the two spins are arbitrary, and therefore all spins should have exactly the same correlation. All right? Okay. And that is the meaning of the long range order. But at the transition, similar situation happens, which means that you have certain form for this correlation function, and that is usually a power law function of the couplings and temperature and so on. But at the transition, the correlation is diverges, and no matter how far away these two particles, two spins are, they all show a same power law correlation functions. And we will see the examples of such critical behaviors in the later part of the course. Exactly reflects this kind of divergence of a correlation length. But here in the Ising model for one dimension, the situation is very, very special and rare in the sense that the transition occurs exactly 0 temperature where spins have long range order. So in many other cases, the ordered phase is not exactly linked to the phase transition. So remember the phase diagram that we talked about at the very beginning of the course, that we have a finite temperature transition, which is what we study here, and we have also a 0 temperature phase transition, which we call this a quantum phase transition. So usually the 0 temperature ground state of some systems which shows some long range order, but this phase does not automatically link to the critical point or transition temperature. But here in the one-dimensional Ising model, the temperature that the spins ordered exactly at 0 temperature. And also that 0 temperature is also a transition temperature. Okay, so that makes the one-dimensional Ising model very special. But in general, the ordered temperature is not exactly at 0, and we may have some finite temperature phase transition in a more general case. So let's take a break here, and when we come back, we will continue using transfer matrix approach to calculate Gij, and we will get the same conclusion, and then we move on to the Landau's mean field theory for this kind of system. See you next time.